Hello and welcome to this series of lectures on basics of control systems in the course on electric vehicles. My name is Ramkrishna. I am a professor of electrical engineering at IIT Madras. So, we will continue our discussions on state space methods. So, at the end of previous lecture, we talked about state space formulation. Why is it a different kind of representation, and our motivation also started by looking at certain examples of systems and what we would like the systems to do. And before we want the system to behave in a certain way, or before we force it to be in a certain way, we would want to know how the system looks like, or what is the system representation. So, we started off with transfer functions and we looked at state space, we looked at what stability means in the context of state space, and also what's the relationship between state space and transfer functions. So, today we will talk a little bit about what can I do with this representation, what hidden information does this particular notion of state space representation has. Of course, we'll try to keep the analysis as simple as possible, and also which is useful for the context of this course. So, again, what are these control problems, and especially when I talk in the context of an electric vehicle. Typically there are several states that we may want to control. An obvious thing that we may look at is the vehicle speed, which may correspond to a motor speed, a corresponding motor current. What is also of use is what is also of interest is the state of charge of the battery, and how would you control or even estimate that. We are looking at battery temperature. We also look at the DC link voltages and several other things across domains that you may want to control. As we started off with say temperature of a room, we had the water level control in a tank, and so on. So, how does this control actually happen, or what are the control commands that we need? Right, it could be some command which should generate an appropriate torque or an equivalent amount of acceleration. We also looked at what happens in the buck converter. We were looking at the duty cycle. How do we appropriately time our inverter switching? Can I control the motor torque? Can I control the charging current? Can I control heating or cooling power, and maybe a flow in case of a water network, and so on. So, the question that we can ask ourselves is, can we use these actuators to achieve, say for example, the desired vehicle state. State here could mean not just the speed, but several other things in terms of the battery, in terms of the motor currents, and so on. Okay. As a simple example, of course, this is a very small example, but is good for us to motivate our case. So, state of charge control is a method of adjusting the electric current to move the battery to a target energy level and keep it there safely. So, it's almost like maybe I'm charging my cell phone battery, or I'm charging my EV battery. So, before control, I need to have a simple model of the battery. So, let me define X as the state of the charge. So, Q is my battery capacity in mAh and so on, and U is the input current. So, how fast or how slow the battery charges can be captured by the input current over here. And what is the objective? The objective, again, if I take a cell phone and I plug in an energy source, the objective is to make my battery state reach a target value. Maybe I just in an ideal case, I just plug in my battery. I want it to say zoom from 0 to say 90% charge as maybe in a fraction of a second. So, objective here is to make the state of charge reach a target value as quickly as possible. Of course, here we will not really look at constraints, but I may have some constraints on what is my minimum current, and also my state of charge will also have some kind of a I'll call this SOC minimum, a regular SOC, and SOC max. Okay. And of course, there are things which we have to tell the model that the state of charge cannot be negative, and if I am measuring it in terms of percentage, it cannot be more than 100%, and so on. But here I think it's kind of easy to check that I can, based on how large or small my u is, I should be able to control the rate or I should be able to control the state of charge, right, and also as quickly as possible too, right. So the idea is to reach from say uh, a state of charge 1 to a state of charge 2, maybe from 10% to 90% in some finite time. Okay, so now if I look at okay, in my state space representation, what is a hidden information, right? So if I say does a solution exist, right? In many of these situations, we just ask ourselves, does a solution exist, or does a controller exist that will stabilize the system? Does a controller exist that will eliminate the steady state error and so on? So if I look at a simple scalar system where where there is only one state of interest, so one state that defines the entire system. Okay, how do I find a solution? So your typical solution would be I integrate both sides, and okay, how do I do this? A simple series of steps would lead me to something like this, right? So x of t will have a component based on the initial condition and a component based on the input. So this is also called the natural response of the system. And this particular thing is called the force response of the system. Okay, so this is essentially like solutions of differential equations which we would have learnt in several other courses. I will not go into the details of this, but the steps here are pretty straightforward to follow. So if I just take a simple say RL circuit, I have a differential equation now of the form x dot is A is minus R by L times x and the input function, which gives me a solution of this form. Say for certain value, say if the initial current is 0, then it just goes on to a value which looks like this. Okay, so this is the basics of how do we solve differential equations of a single variable with some forcing term. Now, if I have more than one state, then what happens? Here is kind of okay. So from my previous calculus experience, I would know how e power at looks like, right? Now, if I go from to a multi-state representation, A is no longer a scalar. So these are matrices. This is also a matrix, and I'm maybe assume that here the system has just one input. Okay, so so my solution now becomes x of t is again something to do with the natural response. Right, when there is no input to the system, right? It's also called as the impulse response, and then the force response when there is certain input to the system. Okay, now I can simply know how to calculate e power minus t, for example, right? But here what sits on top of e is a matrix, say 1 0 1 minus 1 kind of matrix t. What does this mean, right? So we'll maybe look at quick way of computing e power at. We also call this as the state transition matrix. It just gives me information of given a state, given a certain value of the state at a certain time, how will it transit in time. So I'll have so I'll just use a simple Laplace transform method. So I have x of t is a xt. So s x of s is a x of s. So I just look at e power at here is the inverse Laplace of si minus a inverse. Okay, so so my solution would look for a differential equation of this form will be x of t is e power at x naught, and in the Laplacian domain I can just compute the e power at in this way. Okay, good. So what do I do? So I have the matrix A. I compute Si minus A, I take the inverse of this, which will look something like this, And now this is in familiar domain. If I know what is the Laplace, what is the inverse Laplace transform. So I just do partial fraction decomposition. So I have s plus 3 by s plus 1, s plus 2. Can maybe write this as sum a over s plus 1, b over s plus 2. I compute a and b using the standard methods to take the inverse Laplace transform and get it in standard format like this. So, and of course, most solutions are of, will have the exponential terms here as in many of our earlier cases of solving differential equations. Okay, so now based on this, what is the notion of controllability, right? So I have the states here, I have these matrices, I have the input vector, I also measure the output. For now, I will not be worried about the input. So in general, I am looking at a solution of the equation to this of this form. Okay, so we will see now what this means in terms of controllability. So a system is controllable at time t0. Let us for simplicity assume it is the initial time is 0. If there exists an unconstrained control signal, I don't really worry about how large the input value would be. That will take the system from any initial state to any desired final state in a finite time interval. Say it could mean that, say I have a initial speed of 20 of the car, can I go to 80 km per hour from 20 km from hour? Say my battery is at 10% charge, can I make it to go to 90% charge with the help of some control input in finite time? I don't want, I also want my battery to be charged in some finite time, but I don't want to wait like 2 years or forever for it to be charged. Okay. Now, if such an input to a system can be found that takes every state variable from a desired initial state to a desired final state, the system is said to be controllable. And again, so we have a desired initial state, I have a desired final state, then the system is said to be controllable, right? And if I can control the system, I can do a bunch of things with it, right? I can control the speed, I can control the state of charge, I can control the currents, I can through the duty cycle, I can control the output voltage and so on, right? So if the system is controllable, which also means, we will see what this also means, that I can place the poles at arbitrary locations. I can maybe make the system respond faster, I can maybe eliminate errors and so on, right. So, and again, the definition only requires that the input should be able to take my system from the initial state to the final state. How it goes doesn't really matter. Of course, that's a matter of some other course. But here, if I'm going from point A to point B, I'm okay going like this, right? Doesn't really matter. Or I can take a straight line. I can do this way and so on. The trajectory is not specified, and it's not also important at the moment for our qualitative analysis. So my thing is, can I go from initial state to the final state in a finite time interval with some unconstrained control signal, right? If it's as good as me designing a car which goes from Chennai to Delhi in 1 hour. Is it possible? The answer is yes. Can I build a controller like that? Well, that's a different question, right? So, can I build an engine or things like that which will take me from Chennai to Delhi in 1 hour? But at the moment, I assume that I can build an engine which can actually do that. Okay, then how does uncontrollable look like? Okay, so if I take this little circuit and if I assume that this thing holds, and it's kind of a balanced bridge. So if there is no initial charge in the capacitor, say the initial conditions are 0, then okay, the potential across this and the potential across this are the same, right? Which means there is no voltage drop across the capacitor and therefore no current through this. So here I will be 0. And when there is no current, it has no effect over the voltage across the capacitor. Say here instead of a capacitor, say I have a battery and I have a circuit like this to charge the battery. You will never be able to charge the battery because there is no current flowing through that part of the element here, right. So, this system, or more precisely I not write down the state equations that do this, should be simple to write, but what we can see from here is that this system is not controllable. I cannot take my charge of the capacitor say from say 0 to 100. Okay. So, this is one example of a system which is uncontrollable. I am unable to drive the states from point A to point B. Okay. Now, second, so this system has also two states. I can write down the Kirchhoff's voltage laws. I can write down the system in this form, right. So, I have dx1 by dt, dx2 by dt, I have the same elements across a diagonal and an input. Okay. So, let me maybe do some simple case here, right. So, I have x1 dot, x2 dot is, let us say all values are 1. So, I have -1, 0, 0, -1, x1, x2 plus 1, 1 times u. Okay. So, what we see here is that the input kind of enters both the states x1 and x2. Okay. But whatever I do here, what we will see is that the voltage across both capacitors will be the same, because both equations are the same. If I apply u equal to 1, it enters in the same way as it enters the second equation here, or if both are the voltages of the capacitor, both are governed by the same input, by the same entries of the matrix. So, if this goes to 5 volts, this necessarily has to go to 5 volts, right. Here I was unable to charge the capacitor, whatever happens. Here I am able to charge the capacitor, but if one capacitor takes 5 volts, other capacitor also takes 5 volts, which is maybe partially controllable, but can I arbitrarily make this say 5 volts and this say 8 volts, or some arbitrarily value V1 and V2? That is what we will try to answer. Of course, if I change the value from 1 ohm to 2 ohms, things will definitely change, and that is what we will try to investigate, right. So, what does control mean? Control means that I should be able to drive maybe the charge of the capacitor or the voltage to certain level here. Here I am able to drive the voltage of a capacitor to certain level, but the other capacitor also has to follow the same law. So, when I say completely controllable, what I want is each of the individual capacitors I should be able to drive to the voltage levels that I would want. Okay. So, now how do we qualitatively verify this, right? So, I start with my solutions of this form. So, what I want is that I start from my initial state some x naught, I want to go to a final state. Okay, so let us look at each of these quantities here, right. I know the initial state. Okay, let it be some x naught. I know the final state. For now, just let it be 0. It can be 20, 40, -20, -40 and so on. But for our own methods of analysis here, let me assume that I want to start from somewhere and then go to 0, infinite time. Okay, so I know this quantity here, I know x of 0 here. Of course, I know A, so I'll be able to compute this. I know B. Okay, so what I am trying to solve here is a system of equations with an unknown u. Now, this is okay, right? I am just looking at, does the solution to this set of system exist? Okay, so I will skip some of the computations, but we will get what is the larger idea here. Again, my aim here is not to find an explicit ut, but check if a solution exists. Only if a solution exists, and if I am convinced that a solution exists, I will go to design such a control law. So, our aim is not to find an explicit ut, but derive conditions under which such a ut exists. Again, I do not really want to bring on all my tool set of all the possible inputs, give it an input and check what happens, right. I would want to just look at the system And when I say look at the system, what does the system mean to me? Mathematically, the system just means to me these 4 matrices A, B, C and D. Okay. Now, in other words, when is a given system A, B, C and D controllable? I should not look at any input, output, any initial condition and so on. Give me A, B, C and D, I should know whether the system is controllable or not. So, skipping these steps, what it turns out is the following, that I know B, I know A. So, based on this, and if n is the number of states of the system, I compute this matrix, right. So, I have a B, I have a B all the way till A n minus 1 B. I check the rank of the matrix. Okay. If the rank of the matrix is n, then the system is controllable. It's essentially I am looking at now solving a system of equations which is say Ax equal to B, or say Au. Okay. A will mean different things here, but let me see. So, U is my unknown. I have a set of say a matrix say M1, and I have a vector say small m2. So, U, there will exist a unique solution if and only if M is invertible. Again, I am looking at a single input, single output. So, this invertibility is kind of obvious here, else we talk just of the rank of the matrix being full. Okay. So, now that matrix here turns out to be this one. So, the complete state controllability is guaranteed as long as the rank of the C, this I will call as the controllability matrix. That C must have a rank of n. Okay. So, then these two I can extend this to system with more than one inputs, where the condition will just check that the rank C must be of full rank. The rank of the matrix C is n, or it must contain n linearly independent column or even row vectors. Now, the following two statements are equivalent. So, the pair AB is controllable, and why I use B? B tells me how my control enters in the system or where I can place my actuators. So, when I now say just give me A and B, I will be able to find whether the system is controllable or not by the rank condition, that A, B being controllable also means that the controllability matrix has a full rank. Okay, now let me come back to my examples here. And so, I have x dot is of this form. I compute the controllability matrix B, A, B. The rank of this is 1, right, which is less than the state dimension. So, n equal to 2, rank of C equal to 1, and therefore, the system is not controllable. Okay. We can also see from here, right, does the second variable, or if I say write it x1 dot, x2 dot, U does not have any effect on the second variable. So, if I just write down the equations individually, x2 dot evolves only as 2 times x2. There is no U here. Of course, x1 dot I can control by saying x1 dot is x1 plus x2 plus U. Okay. Even this example now I can go back and check what happens when something like this is true. So, the controllability matrix, I have B and I have A times B, which is minus 1 minus 1. The second column is depending on the first column, the rank is 1, and therefore, the system is not completely controllable. Okay. So, here I can get x1 move to any arbitrary state, but x2 I just do not have any control. It will just, maybe because its x2 dot is twice x2, it has some kind of an unstable behavior, and it will just kind of blow up with time. Okay, so how does that my transfer function now look like? Okay, so the transfer function, if I compute C S I minus A inverse B, let us say my output I measure is x1, the system has a closed loop transfer function with just one pole. Okay, now in the denominator I have a S minus 1 and S minus 2, right, of this denominator of Si minus A inverse, the determinant of it. I would expect that the system should have 2 poles because the number of states of the system is 2. So, this unstable pole, oh sorry, or this okay, this is unstable, right? This unstable pole is cancelled by a 0, right? So, the pole at s equal to 0 was cancelled by a 0 at s equal to 2, which means that this is uncontrollable and cannot be influenced by the input u. That is the same thing, right? This is x dot equal to x2 dot is to x2. Okay. So, when a pole is cancelled with a 0, it can be stable or unstable, does not matter. If a pole is cancelled, the control can no longer influence that particular state of the system associated with that cancelled pole. Okay. And therefore, when I just say transfer function, if I just give you a transfer function of the system 1 over s minus 1, I just do not know if it is controllable or not. Okay. What if I am cancelling some poles, right? So, therefore, a transfer function by itself of a system of this form does not capture whether the system is controllable or not. I only have one state now to control. If I take another example, I get the following, right. So, if A being 1, A being something of this sort, B being of this sort, I get the controllability matrix is of full rank, the system is controllable, the transfer function will have 2 poles. Okay. And of course, there are no zeros in the numerator that cancel all the poles are observable or even controllable, and there is no pole 0 cancellation. So, what we have to check, or what this gives us additional information about controllability, is to check whether there is any pole 0 cancellation. If there is a cancellation, that particular cancellation or the state associated with that, I may not be able to control. And also this says that the transfer function of a system is set to control here is the transfer function of the controllable part. Of the system. Okay, uncontrollable just disappears via the pole 0 cancellation. Okay, now we are still talking of pole 0 cancellation. What does it mean in terms of controllability and so on. We also know that location of poles determines stability. Okay, now if my original poles are unstable, can I do something to make it stable? And we saw with a transfer function of s square minus b, how with the help of a proportional control we could make this system to be marginally stable and add derivative component to make it stable, which means I am starting with a system which has unstable poles and I am putting an appropriate control law which makes my system stable, right. So, if the original system is stable, I can still pull the poles and also call this pole placement, right. The poles can be placed via appropriate locations to stabilize the system or even look at transient performance of the system, right. And we saw there's several things about the transient performance in terms of the overshoots, the damping, underdamped, overdamped, that all depends on where my poles actually sit. So, the location of the poles directly impact, of course, the settling time, the overshoots and so on. It also, the location of poles also decide the system's ability to reject disturbances, and we saw having a pole at the origin or having an integral control action actually helps reject disturbances. Now, what does it mean in the context of state space? So, can we design an appropriate control law which will place the poles at desired locations? So, what is the equivalent of poles? So, the equivalent of poles of a transfer function were the eigenvalues of A. Okay. So, now we saw the equivalence, right. When A comma B is controllable, when the system is controllable, it means that the controllability matrix has full rank. If it has rank less than n, the system loses controllability and there will be a pole 0 cancellation, and therefore controllability is a necessary condition to place all the poles. Say for example, here the system was not controllable and therefore I could not do anything about this pole which was unstable. I couldn't make it stable because x2 dot is not influenced by my system dynamics. Okay. So, Okay, little exercise you can do here. Change the B matrix to 0, 1 and check for controllability. And if it is controllable, ask yourself what magic has happened to make it controllable. Okay, and if it is not, then say, okay, what really changes, right? Is now x2 is controllable, what happens to x1? Is it not controllable? So ask yours, maybe just take pen paper, just derive the controllability matrix. If the system is controllable, justify for yourself why it is controllable, from why it was originally uncontrollable, why it has become controllable now, or if it is uncontrollable, just also justify why that uncontrollability remains the same, even though I have just flipped the way the input enters into the system. Okay, so but then what we say, okay, so for me to place all the poles at arbitrary location, the system must be controllable, right? And also the transfer function of the system was only the transfer function of the controllable part. I only had 1 over s minus 1. I didn't know what to do with the other pole at s equal to 2. Okay, now this will give us our first insights of control problems, or how to solve control problems from a state space point of view. So, how do we change the location of the poles, right? And then if you can change, how do I select, where do I put them? Stability is of course one part, but we also have things which go beyond stability. So, therefore, I assume that the system is completely controllable and that the states are available for measurement, and of course, the control input is unconstrained. Okay, so in the classical approach, we saw of how we place the poles of the system, or how I can use PID control to do certain control objectives. And little bit in deeper into control literature, we just are looking at maybe every system as an approximation of a second order system by looking at the poles closer to the origin. But in the state space approach, I will have the flexibility to place all poles at the desired locations. Okay, so what does this mean when I say I want to place the poles? So I start with a system of the form x dot equal to ax. So my open loop poles are determined by the eigenvalues of the matrix A. My control is usually of the form u equal to minus kx. Right, I take x, I multiply it with some number, some matrix, and feed it back. Now here my assumption is that x is known at all times. Okay, that's what this statement here means, that the state variables are measurable and are available for feedback. Right, so x is measured, it is multiplied with a number k, which is my control law, and fed back to the plant. Okay, under this, okay, what happens now to the poles of the system? Well, with this I just substitute this back, u equal to minus kx into this, and I get a new system matrix which is now defined by the eigenvalues of the closed loop matrix. So, original eigenvalues are the eigenvalues of A, or the poles of A. The closed loop eigenvalues are now, or the closed loop poles are now given by the eigenvalues of the A closed loop. Okay. So, in this, eigenvalues are now decided by, of course, A minus Bk. A is fixed, B is fixed, K is unknown. So, can I choose an appropriate K? Can I design an appropriate K which will place my closed loop poles at the desired locations? Okay. Now, how does that translate to solving a control problem? Okay. So, what I would look at is the following. So, if I know that my poles are to be placed at, say, in a second order case, I want the poles to be placed at -1 and -2. This will result in a characteristic equation of the form s plus 1, s plus 2. Okay. Now, I know what is the desired characteristic equation. Desired characteristic equation is s square plus 3s plus 2. And on the right hand side, I have this characteristic equation which is given by Si minus A minus Bk. And u, if it is a two state space system, u will be of the form minus kx, x is x1, x2, and a minus k will be a minus k1, a k1, a k2 with a x1, x2. Now, can I find appropriate k, which will just solve? I have a polynomial on the right, I match it with a polynomial on the left and find the unknowns. Okay, as a simple example, we will just do a very simple method of just matching both sides of the polynomial. Okay, now given this is my characteristic equation, right? I want my closed loop to behave like this, right? Which means that I have I want my closed loop to be closed loop poles to be at s equal to -1, s equal to -2, and s equal to -3. Okay, or maybe I start with a problem where I have poles. So these are my open loop poles. Okay, now can I do something and say, well, let the poles be at now -1, -2, -2 instead of -1, -2, and -3. Okay, and it's a system with 3 states, so k will be of the form has 3 entries, k1, k2, and k3. I write down the equations in this form, right? With the desired pole locations, I have something like this. Okay, this is the desired characteristic equation with poles at -1, -2, -2. This you will get by doing s plus 1, s plus 2, and s plus 2. Okay, and this is the characteristic equation with the desired unknowns. So now I have two polynomials to compare. I just equate the coefficients of s square, I equate the coefficients of s, I equate the coefficients of s power 0 to get a control law of the form k1 is -1, k2 is -2, k3 is -3. Okay, this once we know that the system is controllable, once we know what the closed loop poles look like, this is just a matter of some simple algebraic computations. Of course, for higher order systems, you may want to look at the Ackermann formula and so on, but again, that's beyond the scope of the current course. But at the end of the course, I'll provide you some references that you could actually go through. Okay, let's revisit our example of the DC motor, which has things of this form. I have theta 1 dot, I have theta 2 dot, I have I, a system with 3 states, and then I ask myself, well, the other day we argued that with the help of controlling the current and the inherent coupling between the current and the theta 2 dot through these cross terms and the inherent coupling between theta 2 and theta 1, I should be able to control theta 1, the position. I should be able to control the angular velocity just by controlling the current. Okay, we will also verify this mathematically. So, let us say I take a small example of this form. All the k's are, say, R is 1, L is 0.5 and so on. I get the system matrices of this form, B of this form, and I check what is the corresponding controllability matrix, with some appropriate computations. This is again, I do B, I do A, B, A square B to get a 3 cross 3 matrix which is of rank 3, meaning that the system is like completely controllable. Okay. Now, suppose the desired poles are at locations of -2, -5, -100. This will be the desired closed loop characteristic equation just by getting at s plus 2, s plus 5, s plus 100. We can just check these computations again. So, we want to design a control which will have 3 gains corresponding to the currents, the angular velocity and the angular position. Again, I just compute the two characteristic equations, compute their coefficients and end up with a values of the corresponding gains of the control law to place the poles at arbitrary locations, which will drive my system to a desired current, a desired speed, and also in some cases I may not be really worried about controlling the position, right? I am just interested in controlling the velocity through the current, and I can just do a state space model which is just two dimensions, right? I don't really worry about what position of my motor is when I want to go at a certain position. Of course, for certain servo applications which we might see, we may need some of this extra control, but again really the problem depends on or the controller depends on what problem are you trying to solve. Okay, to summarize, controllability asks whether the available actuators or the actuating signals to the system dynamics, do they influence all the states of interest to me, and if controllable, can we use state feedback, which we also call as pole placement, represented by u equal to minus kx, to choose the desired closed loop dynamics. Okay, what after this, right? So, here I am assuming that somebody is giving me the entire x. All states are available for measurement. What if all states are not available for measurement? That will be captured while we discuss the concept of observability in the next lecture. So, stay tuned for that. We look at observability, we look at state estimation in the presence of noise and so on. That will come up in the next 2 lectures. Thanks for watching.